All right, this is AP Stats Notes 3.2, Part 1. We're going to break this down into some smaller groups here. So in Chapter 3, we're going to start looking at two different types of data. We've already talked about correlation numbers and what those might look like. So now we're going to look at how do we graph those numbers, and we've already done a few of the scatter plots. So we're going to start out with this one that talks about the miles driven on a car against its price. So what do we notice here? We notice that it looks like these dots are going downhill. So we would explain that as miles driven increase, the price seems to go down, right? As X increases, Y seems to go down. All right, so let's start filling this in. So a linear relationship is a straight line between two quantitative variables, and they're pretty easy. Okay, so a linear relationship summarizes the relationship between those two variables, but only in settings where one of the variables helps to explain or predict the other. So a regression line is a line that describes how the response variable, so remember this side is response variable, so that is the y, changes as an explanatory value, or variable, that's this one, as x changes. And another way we say this is explanatory variable, and we say this is response variable. So any of those words are interchangeable on that line. We often use a regression line to predict the value of y for any given value of x. So we're basically saying once we know x, we can predict y, okay? All right, so a regression line is a model of the data. The equation of the regression line gives a compact, where did that go? Gives a compact mathematical description, and it shows us the relationship between y and x. All right, so here is how we write this equation. So the regression line equation is y hat equals a plus bx. Now, this should look a little bit similar to your usual equation of a line, which is y equals mx plus b. In our case, we've reversed it around a little bit. Remember that this b number here is the y-intercept, or what happens when x is 0. This number right here is the slope, which is rise over run. Slope equals rise over run, which is another way to say the change in y over the change in x's. All right, so that's for our old regular algebra stuff. We're going to take a look at it. In our case, notice that now the slope is here, okay, and that the y-intercept is right here. So it is essentially the exact same equation as you learned before. We've just reversed the terms. We've decided that we would like to know what the y-intercept is first, and then we want to know what the slope, which if you think about it in algebra, that's what we kind of graph first anyway. The other big thing to notice is that there is now this little caret on top of y, and that is called a hat. So we call this y hat. And y hat means it is an estimated y. It is not our true y because we don't really know the true value if there even is one. So in our case, we're always doing a prediction. Regression lines are prediction lines. Okay, so there's a lot of different words for regression line. So let's go over some of those, of ones that you might see for a regression line. So you might see regression line. You might hear it called a best fit line. You might hear it called an LSRL, which is a least squares regression line. Any of those mean the same thing, that estimated equation of a line that goes through my points. All right, in our case, when we are doing our variables, in our case, the x's were the miles driven, and the y is the price in dollars of the car. That's a dollar sign of the car, okay? All right, and y hat means it's estimated. So when I'm using the variable y, I'm saying the estimated price, all right? So one of the other things that I could do when I'm writing out this equation, instead of having to write y hat equals a plus bx, and whatever those numbers are for the equation, we would put in for a and for b. However, it could be easier to just say the predicted price equals a plus b times the miles driven. So notice all I did there was I replaced the letters x and y with what they actually stand for. So the miles driven go in here and the predicted price goes right here. All right, everything else is just a reminder of how it relates back to our algebra stuff. We remember that b is the slope, And we remember that A is the y-intercept. And we always want to include context of what the words are that we're talking about when we're talking about x and y. All right, so here's our first equation. They've already given us the equation of the best fit line, right? So they're saying that they think the predicted price for this exact same problem is 38,257 minus 0.1629 times miles driven. And the first thing they want me to do is identify the slope and the y-intercept of the regression line. So this is just simply, can you identify the two pieces parts, right? So we're going to say that the slope is the number before the miles driven. So the slope is negative 0.1629. And how would we say that? So if we wanted to explain this, we could do this as the rise over a run of 1. Remember, anytime you could do that, you can put it over 1. So rise and run. And we would say, what is this that is increasing? So it's rise over run, so that's y's over x's. So when x increases, so we do the run part first, when x increases, which is miles driven, by 1 mile, what is the y? The price reduces by approximately negative, or reduces by, it doesn't reduce by a negative, so we all need, we have reduces for negative, so it reduces by approximately 16 cents. Okay, that's how we interpret that one. All right, let's go and interpret the other one, which was the y-intercept. So y-intercept is equal to 38,259. It's a y, so it's a dollar amount. And what we would say here is when the miles driven is 0, the price of the car is approximately $38,257. Okay, now in this case, it turns out that our y-intercept seems reasonable, doesn't it? Like if you bought it off the lot, that would make sense that this car probably spent, was priced at $38,000. Sometimes when they ask you to interpret these, one or the other don't make sense, and it's usually the y-intercept. If there is one that doesn't make sense, that's usually going to be the one that doesn't make sense, right? All right, so let's go on to a second example here. We are still using this exact same scatter plot of miles and price. And we're saying we can use the regression line to predict the response y hat for a specific value. So the next thing they're going to do is they're going to ask you, use your regression line or use the graph to predict a price of something. So this is a Ford truck with 100,000 miles driven, right? So one of the things that I'm basically doing is I'm looking at the $100,000 mark. I'm going up to my best fit line because there isn't a dot there. And even if there was, it doesn't mean it's the right answer. It's just one of our collected data points. We want to get up to that best fit line. And then we're going to move it over here and we're going to try to estimate what that is. So from the graph, this is a little bit too much for me to try to estimate. Like I think it's between 20 and 25 grand, but maybe there's a way we can actually calculate this out. So we're going to go back out to predicted price equals 38,257 minus 0.1629 times the miles driven. So we put in the 100,000 miles right there and we calculate it. And what we get is, what do we get for that one? Let me grab my calculator here. So if I plug that in, 38,257 minus 0.1629 times 100,000. And I'm getting 21,967. Is that approximately in the range that it looked like on the graph? Yeah, we said we thought it was between 20 and 25. So this seems to be a realistic answer. So remember, we do want to answer things without our word problems in context. So we'd say the estimated price of this car, of this Ford, is 21,967. So I already said estimated, so there's already my wiggle word of approximately, right? So they can ask you to go ahead and use the graph, but really you're using the best fit line equation, all right? All right, so let's take a look at some predictions. So this is basically a prediction line. It's another word for regression line, another word for best fit line. So we can use a regression line to predict the response y hat for any specific explanatory variable x. The accuracy, though, depends on how much of the data scatter about the line. So would it make sense for me to ask you what would y be when x is -2? Well, that might be a number I can plug into the equation, but it wouldn't logically make sense. How can a car be -2 miles, right? That makes no sense. So we have to be careful that this is in context. So there are some things that make sense, there are some other things that don't. Remember, our best fit line is just our best guess at what line goes through those points the best. Okay, so we have to exercise some caution in making predictions that don't make sense. So one of the words we use for that is the word extrapolation. Extrapolation. And extrapolation is the idea that you are making an estimate well outside of the data points that you collected. So if you've only collected data points that were only collected from, let's say, 0 miles to, in this case, it looks like 147,000 miles, then that's really what your prediction should be about, is it within that range, between 0 and 147,000. If we go too far outside of it, like if they ask us to use the line to predict, let's say 200,000 miles, I have a line for it. I could probably go ahead and plug it in, but is it a good idea? Probably not. So usually this idea of extrapolation is that it's not a good thing to do. Okay, so I'm going to say this is bad. Don't do extrapolation. Okay, so if they ask you to do 200,000, you could say, you know, data points that we collected for this graph was only between 0 and 147,000. That would be about what I'd be most comfortable. Now, if they ask you 148,000, close enough, it's really close to what you collected for. But the second that they're kind of like an outlier point, those are ones that you should say, I'm really not happy to. Okay, so it's the use of regression line for prediction far outside the interval of values. So really close is okay, far outside is not okay. And then the warning, don't make predictions using values of x that are much larger or much smaller than what appear in your data. Predictions should only be made when they fall within our numbers. Okay. All right, so on to this word regression. We've been using it already. In most cases, no line will pass exactly through all of the points in the scatter plot. So a good regression line makes the vertical distances from the line as small as possible. So these are called residuals. So residuals is the difference from an observed value of the response variable and the value predicted by the regression line. So notice that we're going to do the observed y, that's like a coordinate point y, and a predicted y, that's a y hat. Okay, so this is the dot on our graph, or the data point that they give us. This is the point on the line for that same x. Okay, and they're both for the same x. And the calculation for that is just y minus y hat. So let's go take a look at a few of these points that we're looking at. And they want us in example 3 to calculate the residual value for a Ford 150 that's been driven 40,000 miles and whose value is $21,000. So we're going to look for 40,000. So it's like right here. Okay. And in order to do this, I would need to have a coordinate point to compare to the actual line. So they would have had to have told me that there is a coordinate point there, and they have. They have said that when the x is 40,000 miles, the value is $21,000. So we would go and we'd find out about where that point would be. I'm going to put it right about there. And then the big thing that we're trying to figure out is how far off is it from my prediction line? What is this distance? This distance right here is what they're asking me to do. So we're going to write out, and we're going to say that the residual equals y minus y hat, and the y value that we were given was 21,000. And then the other one I'm going to get by actually plugging it into the equation. So how do I plug it into the equation? So I have a y hat of, they already told me the regression line is right here. So I have a y hat equals 38,257, same as before, minus 0.1629, and we're now doing $40,000. So plug that into my calculator. And I'm getting 31,741. 31,741. So we're doing 21,000 minus 31,741. Which turns out to be negative 10,741. That's basically telling us what our error is between the point that we would have plotted, the one that they gave us for 21,000, and what the line would have given us if we would have calculated. So we are off by 10,000. Matter of fact, our line is actually above that data point, right? It is actually a higher amount. So if we were predicting, so we'd say if we predict the price of the car using the regression line, the price predicted is $10,741 more than the data provided. Okay, now there's a second way to say that, and that's to start from the dot and say that the point that you have is $10,741 below the least squares regression line. And that's what that negative actually represents, is that we are below the least squares regression line or the regression line, right? All right, cool. So let's take a look at how this is actually calculated. Now, they don't ask this on the AP exam. This is just for you to understand how this line actually gets calculated. And our calculator does it for us. We do not do this entirely on our own, but here is the basic idea. So different regression lines produce different residuals. So if I'm looking at these data points and I'm trying to draw my best fit line through it, just with my eyes, I might have tried something and said, I think that's the better line for that. All right, so how do we ever decide which one is the best line? Well, we're looking at those residual values. And if I were to take all the residuals below and add all the positive residuals, I would get a 0 because the best fit line should be just as much under the line as it is above the line. So if I add positive resids to negative resids, the total should be equal to 0. But on top of that, I want to make sure that I've gotten how do I make sure that that happens? So what they do is they go ahead and instead of trying to keep track of negatives and positives, they're going to turn them into little area squares so that they're squared amounts. So negatives become squared amounts, positives are already positive amounts, so we're dealing with positive amounts instead. So that's the squared residual right here. So we're going to take that residual amount that was that vertical line, turn it into a square, and we're going to add up all of the residual points to that best fit line. And we're going to calculate the sum of the squared residuals. And then we're going to try a different line and do all the new residuals again and do all the squares and add up all the sums of all the squares and see if it's better or worse than the 46 million. And if it's lower, then that's the better fit line. Now, obviously, this would take an enormous amount of time to do depending on how many points were there to help you fix the line. So our graphing calculator does this. This is why we need you to have your graphing calculators or be using the simulator on the website. And I gave you links for that in the regular resources for our Google Classroom. Okay, so that's basically what they're doing to decide on the best fit line. All right, one of the first principles to look at is how much does it deviate from the pattern. So to do that, we're going to do a new thing called a residual plot. So this is after we've kind of find out, we think we have our best fit line, our calculators told us we think this is the best one. So we're going to now look at a residual plot. So on the left is the original scatter plot, the same one we've been looking at for miles and for price of the car. And then this one is called a residual. So what they've done is they've taken every point, calculated its residual, and plotted it as a point on there. So let's show you what we mean. The very first dot is right here. And notice that it is very, very close to the best fit line. It's a little bit above, and look over here, that's the same residual, and it's just a little bit above the flat line that is always there on a residual graph that goes straight through the center. Okay? If I go and I look at the very last one, let's say this one over here that's at 140,000-ish, it is also slightly above, and that's going to match this one right over here. So instead of having a diagonal, it's almost like turning the line a little bit and trying to calculate the pure vertical lines. Now scale is important here because if this scale is, we have it at 10,000, if we would have made it at 2 or 3, we wouldn't have been able to tell how to read that unless there's values there. So these are still going to be called residual values, and what I can tell by looking at this graph is that when we use our best fit line to try to predict a price of a car based on miles driven, I could be off by as much as almost $10,000 above or below. Look at that residual line, right? And what I want to look for a good best fit line, so these relate to each other, okay, is a residual should have a lot of dots above the line, a lot of dots below the line. The closer they are to the line, the better my estimation is, the better fit it is, and that's going to relate to our last section on correlation. The stronger the correlation would be. Okay, so this is telling me I'm not really that great at estimating this from this best fit line. If sometimes I'm off by as much as 10,000, but there are other times where it looks like I'm relatively close, okay? So what are we looking for? A good residual plot, because a good residual plot will tell me if this is a good fit for my line, for my data as well. So a residual plot magnifies the deviations from the points of the line, making it easier to see unusual observations and patterns. So a residual plot should show no obvious pattern. Okay, and what I mean by that is in our scatter plot, it just looked all random, right? They were all over the place. If you saw something that made a parabola shape maybe, or where the dots are all increasing or something like that, that would be bad. That would tell us that our best fit line is either not the right one, or maybe it's not even a line that should be fitting that data. Residuals, the distances themselves should be relatively small in relation to what we're talking about. And when drawing one, make sure that you are labeling your x-axis and your y-axis. So remember, the x-axis is just a repeat of whatever your x was before. Okay, it's exactly the same, exactly what it was before, but your y-axis is now going to get called residual, whatever your y value is, which would be residual price of the car. Okay, so residual price. All right, that's it for now. We'll add more to this soon.